let's take you to the partial fractions situation. Now, something's not right here. Oh, shooting space. Excuse me. Somebody just came in and I have to go out of my window to go back in to get them in. Okay, we're through. Right, these are the questions. I think there's another one, but I can't remember where it is, where you're going to be looking at telescoping series. And we touched on them yesterday. You know, the basic idea is that you have something, take away something, and you write down the first 4 or 5 terms, and there's a lot of carnage going on. And typically at least 1 or 2 things are left alive at the top, and 1 or 2 things are left alive at the bottom. And depending on what those things are, it either converges. If it does, it converges to the 2 numbers at the beginning. And if it diverges, well, that's the end of the story. It adds up to infinity or whatever. What we're going to show you now is that there are some situations which are telescoping series, 2 things subtracted, but they're not written yet as 2 things subtracted. And we have to use partial fractions as a technique to do that. So this is a version of 14. And we're being asked to find if this series converges or not. And if it does converge, what does it converge to? And it looks like this. Now, the first thing that you might notice here is, and it hasn't happened often, but it does happen now and again. Do you see that this starts with a 2 instead of the typical 1? What's the significance of that? Why isn't it starting at 1?
Because it'd be undefined.
Yeah,
you can't have a 0.
Yeah, you'd have a 0 on the bottom, right? And that's okay. It doesn't change a darn thing. It's there because it needs to be there, but it doesn't actually change anything that I'm about to do. In a different world, if that had been n squared plus 1 or something, I would have started at 1 and tackled it the same way. So what we're going to do here, which I'm calling step 1, is use partial fractions to split this guy into its 2 pieces. And you might say, where does that come from? Well, I hope you've recognized that that's actually that guy, right? So we need to figure out how this fraction can be turned into its partial fractions. And once it's a partial fractions, although I'm putting a plus there, technically, I know what's going to happen. Isn't it going to be 3 and -3 or 2 and -2? I kind of know because it's a telescoping series, but just for general purposes, I'm going to call it that. So we are going to go hunting for A and B. And there are 2 distinct methods that we can use. One of them is called the general algebraic method, which I hope to avoid. Not that it's not that hard, it just takes forever. And if you use that method, you will get the correct answer, but it'll take you, 5 or so minutes to do it. And I want to show you a technique called the cover-up method, which is kind of magic, but it works. And one of the great benefits of this kind of magic method, the cover-up method, is it's extremely quick. So you can convert this into its partial fractions in less than 1 minute, probably 30 seconds. That's how quick it is. If you do the general algebraic method, it'll take you minutes, not seconds, to do it. Now, I'm going to do a couple using the cover-up method, the cover-up method. If you're not comfortable with that method, then I'll show you how to do the same kind of thing, but in the old-fashioned way, right? The general algebraic method instead. So let's get started. This is how it works. I want to know the number A. Underneath A is n plus 1. go over here and cover up the n plus 1. So far, so good. Now, what value of n makes n plus 1 0?
-1.
You plug negative into here, -1 into here, and what do you get? You get 4 over -2. 4 over -2 is -2. Right, let's get the b. Right, it's over n minus 1. Let's cover up n minus 1. What value of n makes that 0? 1 makes that 0. Plug 1 into what's left. 4 over 2 gets you 2. And there are our two guys. Now, they happen to be kind of out of order, but you don't know what you're going to get until you get it. So I've decided to rearrange them like that. Including all the talking I just did, that took less than 1 minute. Now, isn't that a much more efficient process to find partial fractions? Now that we have this fella written down like that, I'll return to the original question, and it's now going to be n equals 2 to infinity. This guy, take away that guy. This is our classic telescoping series that we did yesterday. So I'm just going to plug in 2, then 3, then 4, then 5, until I feel, you know, I'm happy with whatever the answer might be. So if you plug in 2, you get 2 over 1. Take away, plug in 2, you get 1. Then you plug in the next number that's 3, and you get 1, take away 2/4, which is a half. You plug in the next number, which is 4. 4 gets you 3, you get 2/3. Take away.
I have a question.
4. Yes.
On the 2 over n plus 1, wouldn't plugging in 2 make it 2/3?
Thank you. You're right. Actually, now that I see a pattern here, I'm pretty sure I know what the next number is. So that's 2, 3, 4. Let's do 5. So that's going to be essentially 2/4, and this guy's going to be 2/6. You can see the little pattern now, can't you? If I do the next one, even without calculations, it would look something like that. And then you imagine, keep going, and imagine that's some random place along the journey. Now, with all telescoping series, don't things get killed off by things? So let's see who gets killed off by who. Won't that negative 2/3 be killed off by that positive 2/3? Won't that negative 2/4 be killed off by that one? Won't this one be killed off by that one? Can you imagine that they're going to get killed off? And the direction is this guy with that. So you imagine this guy gets killed off with that. So what would that tell me that would be left alive? Do you notice that on this side, these two numbers are left alive? And technically, there's two guys here. It really doesn't matter that I don't know the second one, but I can tell you who the second one's going to be. Wouldn't it be the one over here? Now, how do I know that? If two guys on the left live, two guys on the right live. There's always a balance. Now, if that's this guy, won't the one just before it be n plus 1? So now, can you see what's going to happen here? Don't know. Yeah. I went one too far. That guy should have been this. Now, I guess it's because I'm thinking of this line. Would you agree that these two terms disappear to 0 as n becomes infinite? Right? Isn't 2 over n plus 1 infinity, 2 over n, and 2 over infinity, that's 0. So the answer is 3. Not only is it 3, I know it converges to 3.
I'm a little confused of how we got the dm minus 2n.
This fella? Okay. You had a negative 2 over n plus 1 here, right? Here you had a 2n minus 1, right? And you're saying, I'm not sure how I got this guy that goes here, right?
Yeah.
But if you look at this pattern, if this guy is 7, isn't the one just above it 6? And the one just above it is 5. So if this is n plus 1, won't the one above it be 1 less than that?
Oh, okay.
So that's where it's came from. Are we good with that question? Thumbs up. Let's move on. Show you another one. See what 15 is like. Nope, 15 is a different situation. This is like 16. Okay, so let's do the partial fraction part. Okay, cover up method about to happen. Let's get the number for a. Underneath it is n, so you cover up the n. And then you say what value makes n 0? N equals 0. Makes that happen. Plug it in here. 12 over 3, that gets you 12 over 3. That gets us 4. Let's get b now. N plus 3 on it. Cover up the n plus 3. What makes n plus 3 0? Negative 3 makes it 0. 12 over negative 3 gets you negative 4. This is a very, very special case. Do you know that these are going to be telescoping series? See if I figure out this number's 3, can't I just put minus 3 in because I know it's going to be it without actually doing it? If this is 5, won't that be negative 5? If this is negative 2, won't that be plus 2? Because in a telescoping series, aren't both fractions got the same top number? One is plus and the other is negative. So in a way, that even cuts down my workload even more. Don't I only need to find one of these two because I know the other one is the same number but plus or minus it? Are we cool with that? Where the 4 and the negative 4 came from? So we can now do the telescoping series part. If you plug in 1, you get 4 over 1, take 4 over 4. Then you get 4 over 2, take 4 over 5. Then you get 4 over 3, take away 4 over 6. Then you get 4 over 4, take away 4 over 7. You get 4 over 5, take away 4 over 8. You get 4 over n and 4 over n plus 3, right? This guy gets killed off by that one. This one gets killed off by that one. Can you trust me that that one would disappear down here, that one would disappear, and that one would disappear, and this one would disappear? Which means there is a 4 over 2, and a 4 over 3 left alive. Technically speaking, won't there be 3 terms left over at the end? And I could write them all down, but since I'm lazy, plus it doesn't matter. Won't they all look like this guy, but 4 over n plus 2 and 4 over n plus 1, right? But don't all of them disappear to 0? So I can take a kind of shortcut and say 4 add 2 add that, what's that? 6, 18, 4, 22 thirds, and it converges. And it converges because those terms disappear to 0, so they don't matter. And these 3 are the only ones that are left alive. So that's in a nutshell, that's basically the telescoping series. Did you see in this one, I had to do quite a few terms before I finally got, oh, there's a kill. But once you get a kill, don't they basically, you know what's going to happen all the way through after that, right? So you may have to do quite a few terms before you realize that those 3 make it out alive. If I was being really fussy about what would the end terms be, that one would work. The one above it would be that guy, and the one above that would be that guy. So I've been really precise. Wouldn't these 3 terms fit in there? But what I'm saying is, aren't all of them zeros? That really doesn't matter, not in the big scheme of things.
So we could just add
Any questions about?
We could just add, like, once we find the ones that are not killed off, we can just add those to find where it converges to without having to do anything about the end. Okay.
Well, as long as that disappears to 0, I don't really care, right? And these questions here, that's exactly what happened. When you deal with questions,
is there like a question where it doesn't converge?
yes. What would they look like? They would look like that. But I wouldn't use telescoping series for those ones. I would use the divergence test because the limit of that is 12, and that means it diverges. So the ones that don't work, the divergence test would catch those. So you're pretty safe in realizing that the ones that you're going to do the telescoping series for, they are going to be convergers. You're really just trying to find out what they converge to. So that's just the rules of the game. If this fraction diverged, right, because it could, this series, I would probably not use a telescoping series to do that. I would be using divergence test instead, for example. Are we good? Okay. Let's see what 18 looks like. Right. Here is a version of question 18. I have a made-up name for these guys. Can you remember what my made-up name for a series that looked like this?
Frankenstein series?
Yeah, right. So it's got an arm from one series and a leg from another. So when you do these questions, you will tackle them this way. You're going to find out if this converges or not. Then you're going to find out if this converges or not. If both of them converge, the whole series will converge. And they will converge to whatever this adds up to plus whatever this adds up to, right? So you'll combine 2 separate answers together. If you find out that this one diverges, do you bother even looking at this one? Because if this one diverges, the whole series diverges. It wouldn't have, but if this one diverged, same answer, right? So let's focus on this guy who isn't a partial fraction. Oh, do you recognize what a partial fraction question looks like, which becomes a telescoping series? Don't they have this number over n plus 1, number over n plus 1, n plus 2 kind of look to them, don't they? Typically, two guys and a number on the top. That's kind of their look. But let's look at this guy. Do you recognize this guy? Because they don't tell you what he is. What kind of series is this guy?
Geometric.
Nailed it. What about it made you notice that it was geometric?
The exponent over the e.
Yeah, there's some kind of power thing going on here, isn't there? Don't geometrics tend to be 4 to the power of n, a half to the power of n, a half to the power of n minus 1? Don't they have some kind of weird powery thing going on? Now, to do this then, don't we need to know a, the first term? And don't you get that by just plugging 1 into here, and the answer ends up being 4 over e? And you also need to know r. Can anybody tell, just looking at that, what r is? Because I'm going to show you how to calculate it if you don't know how it is. But what do you think the common ratio for this one is? Because it's not as obvious as a lot of the geometric series are.
Is it 1 over e?
You nailed it. It is 1 over e. So for those who are not sure where that comes from, if you take this guy and you plug in 1, you get the first term. If you plug in 2, you get the second term. If you plug in 3, you get the third term, and so on. To get the common ratio, don't you take this number, the second term, and always divide it by the first? Isn't that the way you find the common ratio for ugly geometric, right? Ones that aren't obvious. Now, if you take this guy and you divide him by this guy, it's the same as taking this guy and multiplying by his reciprocal, and you can see all the cancelling, and you're left with 1 over e. Now, is 1 over e going to result in a convergent geometric series? Right, the absolute value of the 1 over e is 1 over e. Is 1 over e less than 1, I guess, is what I'm asking. Yeah, isn't e about 2.7 roughly? So it's definitely less than 1. So that means it converges, which is good news. And now I need to know what its sum is. Well, it's a over 1 take away r, which is 4 over e all over 1 take away r, which is 1 over e. Now, you might want to leave that answer like that, but style points tells me, we got to make this pretty, right? This fraction has got fractions in it. That is typically ain't going to harm, right? You got to make it look pretty. So I'm going to do quite a common trick in this situation. I am going to multiply this fraction by a special version of 1. Now, what that does is, it's still the same fraction, right? I'm multiplying by 1, so I'm not changing its value. But when I change how it looks, so 4 over e times this guy gets me 4. E times this guy gets me e, and e times this guy gets me -1. Would you agree that is a much nicer looking answer now? Right, that's the style points part done. And so we are just halfway through this question. We have done the first part converges, and it converges to this. And now we focus on this guy. And I'm now going to go dot, 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 dot. Won't this be the cover-up method, telescoping series? It converges and you figure out what it converges to. And then this guy plus this guy is the answer, right? So you will say it converges, and it converges to 4 over e minus 1 plus, I don't know, 3/4, whatever the real answer is for this bit.
Ask.
Question?
For the A, why is it 4 over E?
Okay. This number here, this 4, is that what you're talking about?
I mean, like when we found the A at first, like why do we say it's 4 over
Why is that? If you plug n equals 1 here, you get 4 over e to the 1, which is 4 over e. And that's where this e, this 4 over e came from. It's the value of a. That doesn't sound like it's your question. What is your question?
Like, I'm wondering how we got that A value.
Okay. What I'm saying is that if you take your series and you recognize it's a geometric, which it is, you put n equals 1 into this expression. That gets you 4 over e to the 1, which is 4 over e. And when n is 1, that's the first term, and that's a. When you plug in n equals 2, that would be what the second term would be. N equals 3 would be the third term.
Okay, now I remember.
Okay? Okay, so that's what's going on there. Going to call that one done, although I've only half done it, but you could finish it off. So there are a couple of bits and pieces in this list which are telescoping series, but not the type that uses partial fractions. So let's show you a version of 15. That is a telescoping series. It just doesn't look like one. Shouldn't a telescoping series be A take away B, right? Something take away something else, right? And in this format, it doesn't remind you of that. Is there anything I can do with the log of n over n plus 1 that might help us here?
Could you make it as like a subtraction? Like ln of n minus, yeah.
Yeah. You see that 4 there? I could use it, but you know that you're allowed to stick out constants because it's really getting in the way. And so this and this are equal to each other. You're allowed to pull out a constant, a number, out of a sigma, especially if it's causing trouble. Can you imagine that's a really ugly 4 over 17, and you don't want to have 4 over 17s everywhere, right? They're just getting the road. So just pull the damn thing out. So what am I going to do is I'm going to check that this converges or not. Now, if it does converge, I'll have to remember to multiply my answer by 4. And if it diverges, who cares? 4 infinities is still infinity. Well, ready to go. Plug in 1. The log of 1, take away the log of 2. Then it's a log of 2, take away the log of 3. Then it's a log of 3, take away the log of 4. And then you imagine you keep going, and it's a log of n, take away the log of n plus 1. Let's see who dies. That gets killed by that. That will get killed by that. That one will get killed by that. Since this one is left alive, that one will get killed by somebody over here. It means that we are left with the natural log of 1, take away the natural log of n plus 1, right? That's what would be left over. A guy at the beginning and one guy at the end. Now, what's going to happen to this when n becomes infinite?
It'll go on for infinity.
And that means this diverges.
Or negative infinity, my bad. Because we have
Yeah,
a sign in front of
you're
the
right.
colon.
But yeah, as far as I'm concerned, if it doesn't work, we just stick a label on it called diverges. You know, and there's lots of different versions of not working. Plus infinity or negative infinity are 2 of them. Great. And Here we are. So far, so good. But I think I'm covered. I think we've done everything. Yeah. Okay, so we are now going to look at our next section. So we're going to look at section 11.3, where we are going to do a test called the integral test. I like the name integral test because it tells me what you need to do. You need to find the value of an integral. So we're going to do the warm-up part today, and then depending on how much time we've got, we'll then talk about actually using the integral test to test if a series converges or not. But let's just forget about series for a while and return to Calc 2. One of the things that you're asked to do in Calc 2 is to find integrals, right? Indefinite integrals of type, I think they're called type 2 when there's an infinity here. Type 1 or 2, who cares? Right. Now, can you remember how you approach finding an integral where this limit is infinite? And it's always going to be 1 to infinity or 2 to infinity. You're not even going to get the, the vertical asymptotes at x equal 4. That ain't going to happen. And you're not even going to have negative infinity versions. It's always going to be a number, typically 1 to infinity. And we need to find out what this is equal to. And the answer will either be a number, in which case you will say it converges to 4, or it will be infinite, won't it? It'll be undefined infinite, in which case you just say diverges again, right? Remember, converges, you get a number, diverges, it doesn't work. Well, what we do is we turn this question into the limit as t tends to infinity of the integral from 1 to t of 1 over x squared, which I am going to call x to the negative, x to the negative 3. And the reason I'm going to call 1 over x cubed x to the negative 3 is because if I'm going to integrate that, don't I need a power to use a power rule? So what I'm now going to do, move it over here so I'll get a bit more room. It's going to be the limit as t tends to infinity. Integrate x to the negative 3. Well, you add 1 to the power and you divide by the new power. And then you'll evaluate it at x equals 1 and x equals t. But I'm going to do some style points first. And this is going to become that guy. And I strongly suggest that you make sure you do style points in these questions. Otherwise, later on, you're going to find it much more difficult to answer what does the limit as t tends to infinity look like. Now, in this particular question, it's going to be the limit as t tends to infinity of negative 1 over 2t squared. Take away, plug in that, take away negative a half. So it's going to be the limit as t tends to infinity of this guy plus a half. Now, we've done limits in Calc 1 a lot. We did limits when we came to do this in Calc 2. In this particular question, can't we do what I call brute force, which is basically just make t infinite, and you pretty much know what you're going to get. So, oh, excuse me. I just did a phone call. I'll check what that is there. Okay, where was I? Oh, right. So, if you plug infinity into here, doesn't 2 infinity squared just get you infinity? What does 1 over infinity essentially level out at? Its limit, if you like. What's that guy equal to?
Would it be 0?
Yeah. In which case, this converges to a half. Is that familiar? Does it kind of get some cobwebs out your brain? Oh yeah, I remember doing those guys. Are we good? Sort of. Okay. I think we need another one at least, maybe 2 more. Let's try the next one. Let's find the integral from 1 to infinity of 1 over x. Oh, make it a 10. 10 over x, what about that? Then it's going to be the limit as t tends to infinity of the integral from 1 to t of 10 over x dx. Why am I not turning that guy into an x to the -1 and trying the power rule on it? Because isn't that a special case where you don't do that?
It's easier to see that it's the log.
It's a log, right? If you turned it into x to the -1, wouldn't you add 1 to the power and get x to the 0? And then you'd say, but now I have to divide it by 0, and you'd go, okay, that didn't work out well, right? That's the only situation where you do not convert something to a power of x and then use a power rule on it. Now in this case here then, it's going to be the limit as t tends to infinity of the natural log of x, well actually 10 times the natural log of x, evaluated at 1 and at t. And that's going to be 10 times the natural log of t, take away 10 times the natural log of 1. Okay, brute force again. What's the log of infinity?
Infinity.
Right, and isn't 10 times infinity still infinity? And does it really matter if you take away 10 lots of 0? Don't you still get 0? So isn't this answer essentially infinity, which means that it is divergent? It means that this integral is not a fixed number. It's infinitely large, essentially, in this case. You feeling better after 2? Let's show you a weird one. What is the integral of 1 over x squared plus 1? That's got you thinking. What is the antiderivative of 1 over x squared plus 1?
Wasn't it something along the lines of like tangent?
You're almost there.
Is tan
Go on.
secant? Or
No, you're going further away. The
No.
tangent.
Inverse
What kind of
tangent?
tangent? Yes. You almost had it. Inverse tangent. Evaluated at 1 and at t. So that's going to be the limit as t tends to infinity of the inverse tangent of t, take away the inverse tangent of 1. I know what the inverse tangent of 1 is. It's the angle whose tangent is 1. So can you trust me that it's pi over 4? Right? What angle has a tangent of 1, right? It is pi upon 4. What is this guy? Now you might just say, he's infinity, but he's not. If you sketch the inverse tan function, he actually levels off. Does anybody know what the value of the inverse tangent function is as you approach infinity? In other words, what height does it level off at? Because it is a physical angle.
1.
No. I like 1, it's a nice number.
Is it
but
pi
it's not
over
the answer.
2?
That's the guy. So this one actually converges. The inverse tan of infinity is actually a number. It's pi upon 2. Did you forget about that one? Because it's a kind of rare exception to the usual rule that, you know, the sine of infinity or the log of infinity or, you know, anything else to infinity, don't you typically get infinity out of those situations? But the inverse tan is an exception to that rule. Are we comfortable now with the method of finding integrals that are of the form 1 to infinity? Now you're going to get lots of practice at these because in the integral test, these are the integrals you're going to find. And if the integral converges, your series converges. And if the integral diverges, your series diverges. So let's show you how that works. Does anybody recognize that series? It's popped up about 2 or 3 times this week.
Harmonic.
It's a harmonic. What did I tell you about the harmonic? Didn't I tell you it diverged? And I didn't prove it to you. I just said, trust me, it diverges. Let's do the integral test on it. What does the integral test say? It says, if the real integral that uses the same formula, in this case 1 over n, right, becomes 1 over x, if this integral converges, then the series converges. This is what the integral test says. And if this integral diverges, then the series diverges. In these questions, you're only typically going to find out, most of the time, does it converge or does it diverge? You are not going to get the, and now what does it converge to? You might think that the answer to this integral would be what it converges to. I wish that was true, but the answer is not that. It'll be a number, but it won't necessarily be the same as the integral. And I can show you maybe after this why that's the case. So let's go back to this fella. The integral test is that guy, right? So we know that's going to be the limit as t tends to infinity of 1 to t of 1 over x dx. And darn it, didn't we just do that a few minutes ago? That was one of my 3, but I'm going to zoom through it because I've already done this fella. So you integrate a 1 over x, you get a log. If you make t infinite, this thing is infinite because the log of infinity is infinity, and so it diverges. So I have now proved that this series diverges by the integral test. You normally tell people what test you used to prove something converges or diverges. So I've used a test called the integral test to prove that this diverges. So how about me trying to explain how on earth this process works? Imagine that you chose as an x-axis the numbers 1, 2, 3, 4, and you got the value of 1 over x. Well, it'd start off at 1, right? And then it would be a half, and then it would be a third, and then it'd be a quarter, and then it would be that. If you imagine these single points and you join them up, basically, isn't that the curve 1 over x? Now, the sequence only takes snapshots along the journey. But can you imagine that you built little strips, and those little strips then become rectangles? Won't the area of that rectangle be the value of the first term? Because it's 1 times its height. Then it's 1 times its height. So won't all these guys represent the area of that thing? Now, if the guy is infinite, if the area is infinite, won't these rectangles be infinite when you add them all up? So if the area under the curve is infinitely large, won't this series, which is made up by adding these rectangles, also be infinitely large, and so it diverges? Now, if the area under the curve is a finite number like 4, won't all these rectangles add up to a number that's also finite, but won't it not be 4? Won't it be a little bit different because the rectangles aren't the same as the curve? So that's why it's not a perfect match. What it does tell you, which is all you're really interested in, yep, it's going to converge to something, or nope, it's diverging because it's infinitely big. And that's essentially what the integral test job is, to tell me if something converges or diverges. It's not going to tell me directly anyway what it adds up to when it converges. We'll see next week how we can estimate for the converging ones what it adds up to. And that actually ends up being another integral, but we'll worry about that. And you've already beaten me to it, so thank you. Will you, the rest of you who haven't said, will you say hi? And bye-bye. I'll see you next week. Have a great weekend. Try and keep up with your homework. Don't have a quiet week, because that'll make next week horrible, right? So make sure that you do as much as you can now, so that you have less work next week.
Thank you.
You're welcome. Bye-bye, guys.
Have a good one.
You too.
Professor, I have a quick question.
Oh, sure. What you got? Yes, stop.
For number 10, for 11.2.
Okay. Number 10.
The series of 1 over 4 plus e to the power of negative n.
Oh, sorry. Right. It's right. Say it again. I'll just write it down.
Oh, 1 over 4 plus e to the power of negative n.
Is that what you said?
Plus 4 plus e to the n. Oh, I'm sorry. I should have.
It's hard to say in English. Right? Let's try again. Okay, go.
Yeah. Okay. So it's 1 over 4 plus e to the negative n.
Okay, gotcha.
Yeah.
We're cool. I'm going to do a divergence test on this. My screen is really white.
Okay.
I don't know if it's really white for you. So, divergence test is you find the limit as n tends to infinity of this guy. What will this guy look like? Yeah, that'll work. Okay. I can do brute force on this one. Here goes. Okay. E to the negative infinity is the weird part. Isn't that the same as 1 over e to the infinity? Isn't that 1 over infinity? So that's 0. So this guy becomes a quarter. And according to the divergence test, if it's a number, it diverges. In this case, it's a quarter.
Okay. Okay. Thank you.
Okay. Any other questions before I go, guys?
That was a lot simpler than I thought.
Oh, well, that's always nice, isn't it?
Yeah.
Sam,
I do have
you got a
another
question?
Yes.
Sure.
And
What you got?
So it's not from the homework, it's from a couple lectures ago. I tried to figure it out after class, but I couldn't. So the harmonic series diverges, but
Correct.
there's geometric series that converges. It's the frog problem.
Yes. Okay.
And I'm wondering what the difference, like why the geometric series converges.
Right. So the frog one would be this guy, I think, right? Or maybe an n minus 1, right? I think that's the frog one, right?
Yes.
And so the question is, why does this converge?
Mhm.
Is that what you're asking? Right.
Versus why the other one diverges.
Well, let's focus on why that diverges. First, I've just done the integral test, which proves that it diverges. Well, at that point in time, you didn't know that. So what I said is, you have just got to trust me that this diverges. So here's a pseudo proof of why this diverges.
Mhm.
You can take the first term, which is 1. Okay. If you add up the next 4 terms, you will get a fraction that is a little bit bigger than a half. Would you agree?
Yes.
A little bit harder to do the next one. But if you add up the next 8 terms, so a 6th, a 7th, an 8th, a 9th, a 10th, can you trust me that they also add up to a fraction that is a little bigger than a half? If you then add up the next 16 terms, you get a fraction that's a little bit bigger than a half. Can't you, because it goes for infinity, can't you do that process forever? So what do you get? You get a 1 plus an infinite number of halves. Doesn't that add up to infinity?
Okay, that makes sense.
So that is the proof of that. Now, why does the geometric series work? The geometric series works, well, first the test says it does, because in this case, isn't the guy a half, right? And if the ratio is less than 1, it converges. The proof of that, you might want to go and look online for it, but essentially, it's a limiting process. It says, as long as r is less than 1, these terms get smaller quickly enough that they don't build up to an infinite amount.
Okay. That's good enough for me. Thank you very much.
Okay, you're welcome. Any other questions?
Could you do the cover up method one more time? It's the first time I've ever seen it.
Okay, let's do one. 10 over n minus 1, n plus 1. Probably have to start at a number like 3 just to make sure you don't get any weird values. So the cover up method. One of the terms is this guy, the other is that guy. So it's made up of these two guys, right? So let's find the a, the number that goes above n minus 1. You cover up n minus 1. And then you replace what's left here by 1. The number 1 is because that's what makes this 0. So 10 over 2 gets you 5, and this guy is 5. So do that again. N minus 1, cover it up. What number makes n minus 1 0? The number 1 makes n minus 1 0. 10 over 1 plus 1, 10 over 2, 10 over 2 gets you 5. Right, let's try the second one. The n plus 1. Cover up n plus 1. What value of n makes that 0? What value of n makes n plus 1 equal 0?
-1.
Right? Plug in -1 to here, the bit that's left. 10 over -1 take away 1. 10 over -2, -5. Need another one?
Yeah, I think I need another one.
Okay. 6 over n plus 2, n plus 3. Let's get the a, right? The number that goes here. N plus 2, right? I guess I'll put the a and the b in to be consistent. Cover up n plus 2. What value of n makes n plus 2 0?
-2.
What do I do with that -2? I plug it into what's left here. 6 over -2 add 3. 6 over 1. 6. N plus 3 guy. Cover up n plus 3. What number makes n, what value of n makes n plus 3 0? And the answer is -3. Right? -3. Plug it into here. 6 over -3 add 1. -6.
Okay, I see it now. Makes sense.
Yeah, you might want to just, you might want to just randomly pick a number and 2 guys at the bottom. Don't make them too far apart. Make them like +1 and -1, or n and n plus 1, so the numbers don't get too weird on you. And just practice doing this until you feel comfortable.